Yes, dear viewers, I'll welcome you back. And in today's lesson, we are going to look at the factors that affect solubility of sparingly soluble salts. And after this, we are going to look at the experiments that can be carried out to determine the solubility of sparingly soluble salts. And if time allows us, we are going to also look at a few calculations that connect to this so that we see. And when we talk about solubility, the introduction was covered in lesson 1, which will be posted soon. But basically, when we talk about common ion effect as one of the factors that affect solubility, I want to bring it in this form, whereby you're having a sparingly soluble salt, maybe AX. Before we look at the definition, look at a sparingly soluble salt, AX. And this sparingly soluble salt is in liquid form. If you add aqueous to write the equation for solubility, but you can do away with aqueous, an equilibrium will be established in the saturated solution, whereby we shall form the ion of A, and this will be in aqueous state, and we shall also form the ion of B, which will be in aqueous form. So when you introduce in a more soluble salt, because what we do, we introduce in a more soluble salt or a soluble electrolyte, which has one of the ions of these. So for example, if you introduce in a more soluble salt AB, this more soluble salt AB, because it is more soluble or because it is a more soluble electrolyte, it will completely ionize, and in that it will give us A ions and ions of B. So it implies that the concentration of A ions has increased in the solution because you had a sparingly soluble electrolyte which had ions of A, and you also have introduced in a more soluble electrolyte which has got other ions of A. So implying that the concentration of A has increased. It means that the excess A is going to react with the X. Sorry, actually this was supposed to be X here, not B. This is X. So the excess A will react with the X to precipitate AX again. So the excess A having a higher concentration, so A will react with the X, and that will lead to precipitation of AX solid. So basically, when we're defining the common ion effect, we define it as the precipitation of a sparingly soluble electrolyte. You precipitate what you started with. The precipitation of a sparingly soluble electrolyte from its saturated solution by adding a more soluble electrolyte containing one of the ions of a sparingly soluble salt. You make sure that the electrolyte you're adding is more soluble than the sparingly soluble electrolyte. In addition to that, it must be having the ion of the same, it must be having one of the ions as with the sparingly soluble salt. So here we normally explain some observations. And let's have a look at some of the bits. But you must get the definition with you. You precipitate back a sparingly soluble electrolyte by adding a more soluble electrolyte that is having one of the ions as the sparingly soluble salt. So basically, let's see one of the explanations. The question can be, this is a guiding question. I can say silver chromate and this silver chromate is sparingly soluble in water. It's sparingly soluble in water. Explain what will happen to the solubility. Explain what will happen to the solubility of silver chromate solubility of silver chromate when each of the following when each of the following is separately added. One, we are adding silver nitrate. Two, we are adding potassium chromate. So we are supposed to explain what would happen if to silver chromate is separately added silver nitrate and potassium chromate. Well, as you can see, if we had to begin with one, they have told you that silver chromate is sparingly soluble in water. So it's better you first write for us an equation to show us how silver chromate is sparingly soluble in water. So it will establish an equilibrium to form two silver ions and chromate ions. Then what you're adding, silver nitrate, we know that all nitrates are soluble, so silver nitrate is a soluble electrolyte, which completely ionizes, forms silver ions and nitrate ions. So the explanation would be, they want us to talk about what happens to the solubility. So first tell us exactly what happens to the solubility. We are going to find out that addition of any common ion reduces the solubility of sparingly salt, and we're going to derive the idea of how. So first tell us that addition of silver nitrate decreases the solubility of silver chromate. That is a general thing. Whenever you add a common ion, the solubility of a sparingly soluble salt reduces. Why? Because silver nitrate, silver nitrate contains silver ions that are common. Contains silver ions that are common to the silver ions in silver chromate. They are common to the silver ions in silver chromate. You have to first tell us that there is a common ion being introduced. So you tell us that the excess silver ions, added, the excess silver ions added, combine with the chromate ions, combine with the chromate ions in solution to precipitate they combine to precipitate silver chromate in order to restore equilibrium maintaining the value of equilibrium constant, maintaining the value of equilibrium constant. So provided there is a precipitation, it means that you're still forming something which was not well soluble in water. So the solubility has to reduce. Okay, so basically, this is how it works. You add a common ion, the excess of those ions which are common will combine with the other ions of the solution to precipitate again the silver chromate. And that happens because you want to restore the equilibrium. We want to restore this equilibrium that we had at first. So basically, addition of a common ion reduces or decreases solubility. Let's see when you add potassium chromate. Now, remember you have begun with the silver chromate, now you're adding potassium chromate, implying that the chromate ions are going to be common. So if you're describing about this, you'd be having, we have said that we have silver chromate at first, solid, sparingly soluble, to establish equilibrium, silver ions and chromate ions. So we are introducing potassium chromate, which is soluble, because you know that most of the salts of group 1 elements are soluble. So this will form potassium plus chromate again. So basically, still we shall say that addition of potassium chromate decreases solubility, decreases solubility of silver chromate. I'm going to use symbols or formulas, but you can always use words of silver chromate. Why? Because the potassium chromate added, contains potassium chromate added contains chromate ions that are common to the chromate ions in the silver chromate. So what does it mean? It means that the excess chromate ions, the excess chromate ions added combined with the silver ions in solution to precipitate to precipitate silver chromate. Precipitate silver chromate in order to restore equilibrium. Thus maintaining the value, of equilibrium constant. The value of equilibrium constant. So this is how a common ion works. You can, if you want to impress, you can write that equation here, that the chromate ions react with the excess chromate ions will react with the silver ions, basically, and this will lead to the precipitation. This will precipitate silver chromate solid. So this is how it works. For any salt, that is how it goes. So I'm going to put a question for any viewer to try out. And this is explain what would happen to the solubility of calcium phosphate in water when 1, sodium phosphate is added, 2, calcium nitrate is added. So I want you to describe this, and then this one you will be safe with that. So that is a brief discussion about common ion effect. But then we want to also see now, yes, common ion effect in real life, where is it applied? We're going to look at how common ion effect is applied in real life. And then we go to the second factor that affects solubility of sparingly soluble salts. So let's see application of common ion effect, because there are those reactions or there are those processes where common ion effect is applicable. So let's look at application of common ion effect. And one of the applications is the purification of common salt. We have purification of common salt or sodium chloride. So basically, we need to know that sodium chloride basically contains some quantities of calcium chloride and magnesium chloride, and that those quantities that are contained there makes it to be deliquescent. So we are going to find out that the sodium chloride is purified by adding concentrated hydrochloric acid into its saturated solution, which increases the concentration of the chloride ions. What I'm going to discuss it, and then maybe I can tell you how you would phrase it. But you've said that sodium chloride as a solid, it contains some small quantities of basically magnesium chloride and calcium chloride. And a mixture of this in it causes sodium chloride to be deliquescent, meaning that since it has this mixture of substances, then sodium chloride establishes equilibrium to form sodium ions and chloride ions. So what happens is that during the purification of sodium chloride, we add concentrated hydrochloric acid. We add concentrated hydrochloric acid, which forms hydrogen ions and chloride ions. So you realize that since here we have a chloride ion and here we have a chloride ion, the concentration of chloride ions increases and the equilibrium is displaced to the left. When I say the equilibrium is displaced or is shifted to the left, it means that the chloride ions, excess chloride ions, will react with the sodium ions, precipitating sodium chloride. And since sodium chloride was in the left side of the reaction, so it means we are shifting the equilibrium to the left, or we are precipitating again the sodium chloride, and this decreases the degree of dissociation of silver, or rather of sodium chloride, and hence precipitating it, since the solution is already saturated by the sodium chloride. So the main thing here is that the chloride ions, the excessive chloride ions combined with the sodium ions to precipitate sodium chloride, which reduces the dissociation of sodium chloride, meaning basically that is how we purify common salt. So there is no more dissociation of common salt. Instead, we are maintaining our common salt. So basically, you talk about the addition of sodium, or rather of hydrochloric acid containing chloride ions, increasing the concentration of chloride ions, and as a result, the equilibrium will be shifted to the left, decreasing the degree of dissociation of sodium chloride and thus precipitating sodium chloride. Exactly, that is what I'm trying to talk about. Then, application in number 2, we apply it in salting out of soap. Apply it in salting out of soap. So we all know that soap is a salt of sodium or potassium of a long carboxylic acid chain from organic chemistry. And we also know that the process of manufacturing soap, of soap formation, is saponification. So we find out that during saponification, hot concentrated sodium chloride is added to the mixture to precipitate out soap. So it implies that soap is already a sodium salt of a long carboxylic acid, and in its saturated solution, it exists in equilibrium. So soap in saturated solution exists in equilibrium. So we shall have that in its saturated form, soap exists in what? In equilibrium. So we shall form the carboxylate ions, and we shall also form sodium ions. So this is how soap exists in equilibrium. It exists like this. So this R stands for a long alkyl group chain that is added. Now, when you add the concentrated sodium chloride, remember soap itself has already established equilibrium. So addition of sodium chloride, concentrated sodium chloride, will increase the concentration of sodium ions, because this one will be forming sodium ions and the chloride ions. So the concentration of sodium ions is going to increase. So the excess sodium ions will react with the carboxylate ions, basically to precipitate out soap. So basically we shall precipitate back the soap. So it's all about knowing the ions which are common and what it interacts with to cause the precipitation of the other substance you started with. So basically, those are the two ideas that we can have about the formation, about the precipitation of, about the application of common ion. Then that was the factor of common ion effect. But then we are also going to look at the factor of complex ion formation and how it affects solubility of sparingly soluble salts. So the second factor is complex ion formation. So with the complex ion formation, unlike common ion effect, here this one increases solubility. We said that common ion reduces, but this one increases solubility. This increases solubility of sparingly soluble electrolyte or salt. So we are going to see how it happens. For example, I am going to use this with a question, because these questions can appear in observations. They can say that copper 2 iodate is more soluble in ammonia solution than in water. Explain the observation. So that is exactly how these questions can appear, and I'm going to set it in that way. Explain why copper. Here we bring in those substances which can form complexes, because copper can form a complex with ammonia. So explain why copper 2 iodate, is more soluble in ammonia solution than in water. Why copper 2 iodate is more soluble in ammonia than in water. So basically, your statement, the equation will guide you first. We have copper 2 iodate. So we have copper, we have iodate, and this one is a solid. If you add aqueous, you can do away without aqueous, but I love it when it's there. Here you will establish equilibrium to form copper 2 ions, aqueous and iodate ions. Actually, copper 2 iodate, because iodate has valency 1, so here we have a 2, so that you form 2 iodate ions. Now, what does it mean? It means that you first tell us that addition of ammonia solution increases the solubility of copper 2 iodate. Increases the solubility of copper 2 iodate because ammonia solution that has been added, ammonia solution reacts with the copper 2 ions, reacts with copper 2 ions, reacts with the copper 2 ions to form a soluble complex, to form a soluble complex of tetramine copper 2 ion. When you're writing complexes, you don't leave gaps. Tetramine copper 2 ion. Then you write the equation. We have copper 2 ions react with the ammonia molecules, 4 of them, to form tetramine NH3 4. This is tetramine, then 2 plus aqueous. Now, having formed a complex implies that the concentration of copper 2 ions has reduced. That is the implication. So, formation of a complex lowers. I'm going to say this lowers the concentration of copper 2 ions. This lowers the concentration of copper 2 ions, meaning that for us to replace the copper 2 ions, the copper 2 iodate has to dissolve. Or the copper 2, yes, basically, the copper 2 iodate has to dissolve so that to restore the equilibrium by producing more copper, because the concentration of copper has reduced. So this lowers the concentration of copper 2 ions and more copper 2 iodate. And more copper 2 iodate, more copper 2 iodate dissolves. And why? To restore equilibrium, maintaining the value of equilibrium constant. So whenever there is formation of a complex, the concentration of the metallic ion, that is the metallic ion, reduces. And for you to restore equilibrium, more of the sparingly soluble salt has to dissociate, meaning the solubility increases. It has to dissolve. So that is how it happens. The same applies to when it is about silver. I can bring it in this format still. I can say silver carbonate is sparingly soluble in water explain what happens to the solubility of silver carbonate if ammonia solution is added to its saturated solution. If ammonia solution is added to its saturated solution. So what happens here is that they have told us that the silver carbonate is sparingly soluble in water. So it shall form silver ions and then carbonate ions. So basically we shall know that addition of ammonia it generally increases the solubility of silver carbonate. Increase the solubility of silver carbonate simply because ammonia solution reacts with the silver ions to form a soluble complex of diamine silver 1 ion. That is a complex. Diamine silver 1 ion. You give us the equation of formation of this complex. We say that silver ions plus reacts with the ammonia solution to form, actually since it is diamine, then there are 2 ammonia molecules to form diamine silver 1 ion. Aqueous. Now, this complex formed lowers the concentration of silver ions. So the concentration of silver ions reduces. The concentration of silver ions reduces. Why? Because silver ions have been used in formation of a complex. And more silver carbonate dissolves. More silver carbonate will dissolve to restore the equilibrium, to restore the equilibrium maintaining the value of equilibrium constant. Maintaining the value of equilibrium constant. Actually, you should note that ammonia solution has the same effect on the solubility of sparingly soluble copper 1 chloride. Even if it is copper 1 chloride, provided there is formation of a complex in that substance, then it is the same effect. Finally, still on this, we can talk about a different complexing agent, which is not ammonia, and we can talk about the one of lead 2 chloride. Solubility of lead 2 chloride in cold water decreases. In cold water decreases, but on addition of dilute hydrochloric acid, in addition of dilute hydrochloric acid, the solubility of lead 2 chloride in cold water decreases on addition of dilute hydrochloric acid, but increases on addition of concentrated hydrochloric acid. Explained. So basically, you need to know that in cold distilled water, in cold water, lead 2 chloride is sparingly soluble. So that is what you need to first write. In cold water, lead 2 chloride is sparingly soluble. Then you write the equation. We have lead 2 chloride sparingly soluble to form lead 2 ions and the chloride ions. So addition of dilute hydrochloric acid, because hydrochloric acid will have a common ion with the lead 2 chloride, which is the chloride ions, dilute hydrochloric acid. So addition of dilute hydrochloric acid to a solution, to a saturated solution of lead 2 chloride, to a saturated solution of lead 2 chloride decreases its solubility, because dilute hydrochloric acid contains chloride ions, the chloride ions, you use words, contain the chloride ions that are common to the chloride ions in lead 2 chloride. So what would happen is the excess chloride ions added combine with combine with lead 2 ions in solution to precipitate lead 2 chloride. To precipitate lead 2 chloride in order to restore equilibrium. In order to restore equilibrium, maintaining the value of equilibrium constant, maintaining the value of equilibrium constant. So here is common iron. However, if we add concentrated hydrochloric acid, those are two different things, dilute and concentrated. On addition of concentrated HCl, the solubility increases. The solubility increases because the chloride ions, because the chloride ions present, I can say that are present in a high concentration, react with lead 2 chloride, react with lead 2 chloride to form a soluble complex, to form a soluble complex of tetrachloroprambate 2 ion, of tetrachloroprambate 2 ion. The equation PbCl2 solid reacting with the excess chloride ions to form PbCl4 2 minus aqua. So this is how it works. Okay. So now that is the factor of a complex. Finally, we are going to finish with the effect of adding a soluble compound, but which does not contain any of the ions. For example, let me say we are going to add a soluble compound, but without a common ion. That soluble compound won't be having a common ion. For example, we can say, explain why calcium ethane dioate is less soluble in calcium nitrate, but more soluble in dilute hydrochloric acid. Why is it less soluble in calcium nitrate, but more soluble in dilute hydrochloric acid? So here you see calcium nitrate, this part you will explain it for me. Why is it less soluble in calcium nitrate? This is calcium ethane dioate or calcium oxalate. So it is less soluble in calcium nitrate because calcium nitrate will be containing a common ion which will precipitate back the calcium ethane So this part of less soluble is for the viewer who has watched from the beginning. So me, I want to talk about why is it more soluble in dilute HCl. Remember, this dilute HCl being added does not contain any ion common to this. So I'm going to talk about this part, but of course you need to know that calcium ethane or calcium oxalate in equilibrium establishes, in aqueous it establishes equilibrium, form calcium ions and ethane ions or oxalate ions. Now, we're going to find that in presence of dilute HCl, in dilute HCl, this part is used as we have agreed, but in dilute HCl, we are going to find out that the hydrogen ions of the acid react with oxalate ions to form oxalic acid. We form oxalic acid. What I'm trying to mean is that the hydrogen ions reacts with oxalate ions to form oxalic acid. Now, formation of oxalic acid, because oxalate ions have been used up, they were the ones present in a sparingly soluble salt or electrolyte, and now they have been used in formation of oxalic acid. So it implies that the concentration of oxalate ions reduces. So to restore the equilibrium, more calcium oxalate has to dissolve, increasing the solubility. So what will happen is this will reduce the concentration of oxalate ions in solution, hence more calcium oxalate dissolves, this more calcium oxalate dissolves to restore equilibrium, maintaining the value of equilibrium constant. This increases solubility of calcium oxalate. So when we add a substance, when we add the more soluble electrolyte, but without a common ion, still solubility increases because one of the ions of a sparingly soluble salt will be used in formation of a certain substance, reducing the concentration or reducing its concentration in solution. So to restore that concentration, to restore the equilibrium, more of it has to dissolve, thus keeping the value of equilibrium. That's keeping the value of equilibrium constant. So that is it. Our other lesson will be highlighting the experiments that can be carried out to determine the solubility of sparingly soluble salt. Thank you for listening. See you in another lesson.